Now this whole concept in calculating flux is a little bit abstract, so let's really go after what we're interested in, which is electric field. So first let's talk about what happens if there's some excess charge on a conductor, and by conductor I mean something that has free electrons that can move and carry charge throughout a surface. What's going to happen is all of the charge is free to flow, and naturally it wants to flow to the surface because that's the furthest point away from all of the other charges. So all the charges on a solid conductor, solid being a keyword, is going to be on the surface. I'll talk about what happens in cavities in a little bit. Now suppose we went ahead and we drew a Gaussian surface inside of this solid conductor. What we would observe is there's going to be no charge enclosed. Therefore, this integral of E dotted with dA must be equal to 0. The only way for that to happen is that the electric field inside of a solid conductor must be equal to 0. There's no way for dA to be 0. So that's a very powerful application of Gauss's law. Similarly, if we have a solid sphere and we draw a Gaussian surface on the inside, no charge enclosed, the electric field must be equal to 0. So here we're plotting the electric field as a function of radius. This sphere has a radius of r, so we can see that the electric field is 0 inside of it. Now if we wanted to figure out what the electric field is outside of this sphere, and I draw another perfect sphere outside of it, we're going to say that the integral of E dotted with dA must be equal to the charge enclosed, which we'll say it's Q for this particular guy, divided by epsilon naught. I've drawn a sphere, so the integral of E dotted with dA is just going to be E multiplied by the surface area of the sphere, 4 pi r squared, is going to be equal to Q enclosed divided by epsilon naught. And what we're left with at the end of the day is going to be equal to the electric field is Q divided by 4 pi epsilon naught and r squared on the bottom there, which looks a lot like something that we would have derived in the last chapter, kq over r squared. So now let's take a look at applying Gauss's law for a slightly more complicated object. Here we're going to have an infinitely long wire with some charge on it, and we're interested in solving for the electric field. Now in a case like this, we know from the last chapter that the electric field is just going to point radially away from this wire. There's going to be no electric field pointing, say, in that direction. So the ideal Gaussian surface that we would draw would actually be a cylinder around this guy. Why would we do a cylinder? Well, we want our electric field and our little dAs to point in the same direction, such that E dotted with dA is simply going to become E multiplied by dA. So choosing a cylinder, we've chosen our Gaussian surface such that we can just say that that's E multiplied by dA. How much charge enclosed is there? Much like in the last chapter, we'll say we're going to define some linear charge density, which is going to be the charge divided by the length. Really, how densely packed in are these positive charges along this wire? That's what that lambda represents. So our Gaussian surface has a cylinder with a length L, so the charge enclosed is simply going to be the linear charge density, how dense is packed in there, multiplied by L, divided by epsilon naught. Now I've chosen my cylinder to have some radius, and I know that the electric field is not going to vary along that radius right there, and so I can pull my electric field out of the integral, and I'm just left with the integral of dA is going to be equal to linear charge density multiplied by length divided by epsilon naught. Now let's consider what the integral of dA is. We know that there's going to be no electric field, no flux coming out of this area, so that's going to essentially have zero flux going through it, so we're not going to consider that area. If we just kind of rolled this cylinder out, we would have something that looks like kind of just like a square. This is just going to be 2 pi r, and this is going to be length. So this integral of dA is just going to be the area of this rectangle. So electric field multiplied by 2 pi r multiplied by length is going to be equal to linear charge density multiplied by length divided by epsilon naught. And we can start to cancel some things out here, cancel length out. And what we're left with is the electric field is going to be equal to linear charge density divided by 2 pi epsilon naught. And I'll have my radius down there in the bottom. The direction for this electric field, we know that it's going to be in the radial direction. Now, what made this problem so simple as compared to in the last chapter was first, using Gauss's law, but also choosing my Gaussian surface such that this integral of E dotted with dA was easy to do. If I consider a infinitely charged plane sheet of charge, much like we had in example 21.10 in the last chapter, it makes sense to also draw a cylinder. We know that the electric field is just going to point directly away from that. Again, there's going to be no components, say, in that direction or in that direction or anything like that. If I draw my Gaussian surface as such, well, how much charge is enclosed? Well, it has some sigma on there, some linear charge or some planar charge density, or a charge per unit area. Let me consider my flux, my integral of E dotted with dA. This surface right here, there's going to be no electric field lines through it, so E dotted with dA is going to be 0 for this particular surface. I'm going to have an electric field multiplied by area for this surface over here, and I'm going to have an electric field multiplied by area for that surface over there. So what I'm left with is 2 times the electric field multiplied by area. How much charge is enclosed? That's simply going to be the charge density sigma multiplied by the area divided by epsilon naught. We can see that my areas are going to cancel out, and my electric field is simply going to be the charge density divided by 2 times epsilon naught, which is exactly what we found from example 21.10 in the previous chapter. However, it took a lot more work in that chapter to come to the same expression. We can apply Gauss's law to 2 parallel conducting plates, much like we did in the last chapter. One thing is, on this one, we in the last chapter we had a positive charge density. This one we had a negative charge density. We know that these are conductors, and so these positives are going to feel a force of attraction towards these negative ones, and similarly the negatives are going to feel a force of attraction to the positive ones. So all the positives are lining up on this inner surface, all the negative ones are lining up on this surface, and on this surface over there we essentially have no positive charges, and this one we're going to have no negative charges. Keep in mind that this is an idealized model. A more realistic drawing actually does have some positive charges on the outer edge of the plate, causing some electric field out here, but we'll stick with the simple idealized model for this particular class. You can draw any number of Gaussian surfaces. Let's just take a look at this surface S1 right here. By definition, this side of surface 1 is inside of a conductor, therefore there's going to be no electric field, no flux inside of this guy. This one is going to have an electric field multiplied by the area of the box that I chose, so my integral of E dotted with dA now simply becomes E multiplied by area. How much charge is enclosed? Well, much like in the last one, it's a surface charge density, so it's going to be the surface charge density multiplied by the area of my box divided by epsilon naught, and I can cancel out my areas, and what I'm left with is the electric field is going to be equal to the charge density divided by epsilon naught, which agrees with what I found in the last chapter. You can convince yourself by looking at surfaces 2, 3, and 4 that you can do the same things and figure out that the electric field outside must be equal to 0, and surface 4 will give you the same result. We can extend this to insulators. Difference between insulators and conductors is insulators, the charge has to stay where it is. It can't flow around as it can with an insulator. And so what that means is we would define rho, kind of a charge per unit volume of the sphere. So we have some charge Q on it, and we divide it equally throughout the volume of the sphere. So really the charge divided by 4/3 pi and big R cubed. That's going to be the volume of the sphere. Now, if I drew my Gaussian surface to be outside, I'm simply going to have all of my charge enclosed, and so my electric field would be the kq over r squared, which we've already derived. Now, however, suppose I draw my Gaussian surface on the inside with a tiny little radius r. Then my charge enclosed is going to be equal to the linear charge density multiplied by this new volume that I've chosen, divided by epsilon naught. And so that's going to be equal to the charge divided by 4/3 pi big R cubed multiplied by the volume of my tinier sphere, 4/3 pi little r cubed. And fortunately, you can kind of see that my 4/3 are going to cancel out, my pi is going to cancel out, and I'm not going to forget to put my epsilon naught here. Now this E dotted with dA, that's simply going to be equal to the electric field multiplied by the surface area of the smaller sphere that I've drawn, 4 pi r squared there. And now we can see that this r squared is going to cancel off 2 of those r's, and I can divide both sides by 4 pi. And really what I'm left with is that the electric field is going to be equal to the charge multiplied by just one single radius r divided by 4 pi epsilon naught, and then I'm going to have big R cubed, so it's going to depend linearly on radius. And so if we kind of sketched it out with electric field along this axis and radius along this axis, there's going to be a electric field is going to increase linearly with radius, and then I'm going to hit the edge of the sphere, and it's going to die off like 1 over r squared. Just imagine trying to do that using the methods of the last chapter. I can tell you, you'd be doing a triple integral. So we can extend this thought process to conductors that now have cavities in them. We've already said right here we're going to have electric fields must be 0 inside of conductors. Suppose we had a cavity inside of this conductor and we drew our Gaussian surface like that. Then what we need to do is this integral of electric field dotted with dA must be equal to 0, no charge enclosed, therefore the electric field will be 0 inside of the conductor. Suppose we decided to be tricky and go ahead and put a positive charge inside of this cavity, then what's going to happen is the electric field must still be 0 inside of this conductor. So what's going to happen is some negative charge is going to be drawn towards the positive charge to cancel out my integral, such that the electric field enclosed by my Gaussian surface is going to be 0, and the net positive charge on the surface is going to increase in response to that. Why no electric field inside of conductors? If you can kind of imagine, as soon as you put an electric field inside of a conductor, the charges are going to start to shift around, and really not having an electric field inside of the conductor, it's kind of levels the playing field. If you put an electric field in a conductor, then these charges would move to try to cancel it out. A fellow by the name of Faraday did a nice interesting experiment with this called the ice pail experiment, and really confirmed the validity of Gauss's law. All he did was he took a charged ball, there was some positive charge on there, with an insulating thread, so the charge is not going to flow through this through the thread, and he lowered that into a metal container on an insulating stand and put a metal lid on it. And what he proved was that the charge induced on the outside of the pail must be equal to the charge that was lowered into it. Essentially, he was drawing a Gaussian surface and saying, my Q enclosed must be a constant. Then what happened is he was able to touch the ball to the interior surface. Once the ball touched the interior surface, it's part of the interior metal surface of the pail, and all of the charge flowed off of the pail and to the surface of the container, giving no net electric field inside of the container, as we expected from Gauss's law. A Graaff Generator, we'll play with one of these in class, operates on the same principle that all the charge must flow to the surface. Essentially down here we have a motor that's generating positive charge. Essentially think of it as rubbing your feet together or rubbing the glass rod to the fur, and that charge is carried up an insulating belt. It touches the conducting shell, it rushes immediately to the outside of the conductor. Charge must be conserved. Negative charge is going to flow down the insulating belt and go out to the ground. And it turns out that we can build quite a bit of charge and get some rather large electric fields on the outside shell of this guy. And having large electric fields means we can actually have a lot of voltage, kind of getting a little ahead of ourselves with the discussion of voltage. We can also use this concept that the electric field inside of a conductor must be equal to 0 to create an electric shield, also known as a Faraday cage. If we consider a conductor inside of an electric field, here all of the negative charge is going to be attracted to this side simply because the electric field is flowing in that direction. All the positive charges are going to accumulate on this side, and it's going to set up an electric field that is going to cancel out that electric field, and we will have 0 net electric field inside of the conductor. What this means is we can create a shield such that we can try to shock someone with a huge Graaff generator, and that person will be relatively safe. That's also the reason why the safest place to be in a lightning storm is inside of your car, because you're inside of a conductor. It's not because the tires are insulating you from the ground. If you think about it, that the amount of voltage it took for that charge to jump from the cloud all the way to the ground is quite large, and surely it can go through half an inch of rubber with a bunch of steel mixed in there. So really you're protected because the electric field inside of a conductor must be equal to 0. It's worth noting, just very briefly, that the electric field at the surface of any conductor is always going to be perpendicular, and is always going to have a magnitude of the surface charge density divided by epsilon naught. So that's true for any conductor. It starts to become more complicated as we are looking at further radiuses or more complex shapes. But if we just kind of draw a Gaussian surface like this and we say what is the surface charge density right there, the electric field is always going to be equal to the magnitude of the surface charge density divided by epsilon naught.